everybody. My name is Andy Rivenes. I'm a product manager with Database and Memory, and we have a special guest today, Auro Mishra, who is one of our development managers and who's actually one of the primary architects, I guess probably the primary architect of in-memory expressions, which is today's topic. So I have up here, I can try to go full screen, I don't know if it matters, our landing page, which you all have obviously hit to get here, but I always like to remind you that we have our previous office hours sessions here below. So if you want to go look at maybe the original in-memory expressions or some of the things we'll talk about with 21C, we've done some sessions. So you can go look at those over on the left side here. And on the right side, our blog, which I'll probably refer to, our resources page we have, and some other links that you can use if you want to find out more about database and memory or try it out for yourself in our Live Labs environment. And so that's available to you. And so I always like to point that out before we get started. So I'm gonna go ahead and move that down. And we'll do a few slides, and then I have some demos. Auro and I were working, actually yesterday even, on some of the demos and talking about what we were going to show, and it's on my VirtualBox, and my fair warning that it hasn't been that reliable. So I did print out a text file of everything, but we'll cross our fingers, hopefully not jinx it, and the VirtualBox will run, so we can actually, rather than doing slides, I'll show you some demos of how in-memory expressions works within Oracle database and memory, and then how some of the new features that we've introduced leveraged in-memory expressions. So with that, my Twitter handle and email address, Auro graciously volunteered to have his email address up there as well. But the point is, since this is an office hours session, if you have questions, if you're not comfortable asking them now, or perhaps you think of something later, feel free to email either myself or Auro, and we'll certainly be willing to answer what we can for questions about in-memory expressions. Or if you have any other questions about database and memory, feel free, because we'll try to keep this as interactive as possible. So with that, we'll go ahead and get started. And so I did put up here, we are going to cover kind of, I titled it In-Memory Expressions Update. And the idea was that we've talked about in-memory expressions, so there's a link to our features. And I'm going to actually put something I haven't done before, is I'm going to put not only the scripts that I'll use today, but also the presentation in a PDF format on GitHub. So you can go access this, and we have a link on our resources page, which I'll show you. So if you want to go back later and take a look at this and click on any of these links. So in-memory expressions we've covered in the past, the basics, and that started in 12.2, which we'll talk about. We did an office hours on JSON, and so there's information if you want to learn more about how JSON works with Oracle database and memory. And then we did an AskTOM session on 21C new features, some of which we're going to talk about today again, because they leverage in-memory expressions. So if you want to go back and take a look at that, and that's on that page that I showed you also on our landing page, if you scroll down on the left. So we do have other information. So we're building, basically the idea is we're building on top of the previous information, and hopefully you'll get some new tidbits today. One of the reasons I invited Auro, so he'll probably chime in with some things that maybe I don't know about since he wrote it. And so I thought that would be kind of fun. And with that, what's that?
Definitely, Andy.
Okay. Yeah. So just as a review for in-memory expressions for folks, so in-memory expressions were a feature that we introduced in 12.2 as part of database and memory. And the idea, kind of what I like to say is, the fastest ways to do something is to not do it at all. Well, the next fastest way to do something is to only do it once. And that's kind of what the idea behind in-memory expressions is can we pre-compute expressions? Typically, at least initially, was kind of the arithmetic expressions, which I'll show you, populate those in the column store, and then not have to recompute those on the fly as we're accessing the data. And surprisingly, and I'll show you in our examples, that even arithmetic expressions can actually take quite a bit of CPU, since if you think about it, with database and memory now, we're literally using CPU to access memory. And so if we can, to make that faster, either you got to look at less data, or hopefully maybe reduce your CPU footprint to increase your performance. And that's kind of the genesis and the thinking behind in-memory expressions, at least at the beginning. And think of it as, I guess, kind of a framework, since we have new features that we're also using to leverage the underlying architecture of in-memory expressions. So we implement it with virtual columns. There is actually, as Auro pointed out to me, we've talked about it, but I haven't really done a lot of detail about the ability to automatically create in-memory expressions with something called the expressions statistics store. It's actually not part of database and memory. It was actually the optimizer guys within Oracle Database created, but we leverage that to where you can actually set it up to automatically create in-memory expressions, or the most frequently accessed expressions can then be automatically created within the column store and can cycle through. So what at this point, at any given point in time, is the most popular might not be the most popular later. And so those top expressions might actually change. And so with the expression statistics store, a little bit of coding as far as just calling some capturing APIs, you can actually cycle through the most active expressions to improve the performance of your applications. I think that's kind of what I wanted to say. Did you want to add anything?
Yeah, that's right. So it offers you multiple modes where you can capture expressions over a day, or you can specify your custom window, which is something customers really like, because that gives them a lot of flexibility in terms of identifying, okay, this is my representative set, and I'm going to capture expressions from this. And it's going to help me for the remainder of my workload. So it's a pretty powerful feature, which we should definitely talk about at some later point in time.
Yeah, I'll do maybe a blog post, and maybe we'll even do another Ask Tom session. Maybe I can get you, I can talk you into coming and doing that. Actually, it would be kind of cool to do that with, we've done in the past some developer sessions, but get Nigel in, maybe involved and do a three-way. I haven't done a three-way with these three folks, hosts with one of these Ask Tom sessions, but that might be kind of fun. And it goes back to the idea of trying to make Oracle Database more, I know it's an overused word, but I'll use automatic rather than autonomous. But with our automatic in-memory feature, with in-memory expressions, the ability to automate a lot of this work so that folks don't have to monitor their application in order to get the best performance. We can just do it under the covers. And so probably a feature that we should spend some more time talking about, I think. Yeah, but that was one of the things that came out of our preparation for this. So, but I'll continue on in that, and again, the automatic capture. But the gist of this is just the idea that expressions can be captured in the column store, kind of under the covers, if you will, so that we can speed up performance. And I don't want to spend too much time on that, other than since I think we've already kind of talked about it. But and then the question will come up: how do we tell that we leveraged in-memory expressions? And so there isn't going to be anything. Well, it does show up in the execution plan indirectly, and I'll show you that. But really, the way to tell whether you're leveraging in-memory expressions is through session or system level statistics. So I'll show you in our demo. We'll talk about some of the session level statistics that show up, since that's one of the ways that the easiest ways to tell not only how much benefit in database and memory is providing, but also, other than of course runtime, but also what features are getting leveraged. And then in AWR reports, from an overall workload standpoint, you can possibly at least see that your applications are using in-memory expressions if you've defined them. You won't necessarily be able to correlate to actual runtime improvements, which you really can't do with AWR, but you can certainly see that you're leveraging those. And then certainly at the session level, you can identify that, and we'll kind of show that to you. But once you've got it running, ultimately response time is kind of the key. Is it faster? And so that's kind of what our goal is ultimately, is to make queries run faster with database and memory, and then adding in-memory expressions. So I'll move on. So I have a slide here. This will be kind of the one of the for the base in-memory expressions. This is kind of the SQL statement I have as an example. And notice in red, that can actually become then in an expression. And notice that it's just arithmetic on some column values. But as we'll see, the amount of CPU effort to do that, given that we're now running in memory and running much, much faster than we would if we were in the row store, which we've kind of covered in past sessions, this can actually account for a significant amount of the runtime once you are in memory. And so that's kind of what the whole point of the base in-memory expressions feature is about. And so I just wanted to highlight what this in-memory expression might be. And so obviously it could change based on your application and your SQL. And then of course, then the idea of allowing the optimizer to automatically track those, as opposed to you having to look through all of your SQL statements and try to find, stuff like this. So, but this is what we're really talking about. And so okay, so now we're into examples. So I'm gonna get out of this. I learned a new thing. Oh, and of course it's not gonna work. So we'll do that. There we go. And we'll flip over. So I didn't realize if you double click the bar, it goes to full screen. So is that big enough? Can you see that okay, Auro? Should I try to make this bigger?
It's okay for me, but you can make it a little bigger.
Let's see if we can go. Since I'm going full screen, and I was told when we did Database Worlds session that it's better to use full screen rather than I usually do piecemeal. Stephen Feuerstein, when he was doing AskTOM, always recommended it was easier to flip back and forth. But since we'll be here for a little bit, I think this will be good. So hopefully everybody can see that. And so what I've got here is my VirtualBox machine, obviously, but it's actually running 21C, so 21.3. Actually, 21.4 is out, so if you didn't know that. And I have on our resources page some MOS notes to look at the most current versions of, with RUs, since we do apply fixes in RUs. And so we do recommend that you be on the latest version of Oracle Database, whatever your version happens to be, whether it's 19C, which is the current long-term release, which ought to be your target, unless you're looking for new features, which you can obviously use in 21C. And some of the features we're going to talk about today were part of the 21C release. Anyways, not to belabor the point, but 21.3, it's on my VirtualBox. And what I have here is I've taken the liberty of pre-populating objects. I didn't want to have to sit around and have everybody wait to see population take place. So I've already populated data. Our normal SSB schema with the line order, which is our large fact table, which we use for most of our demonstrations, customer, date dimension, part, and supplier are all part of the SSB schema. Now I've added some additional tables. Chicago data one, which is actually what I used in the in-memory full text columns demonstration, and I'll use today again. And I just did a blog post. I released that, I guess, last week, the end of last week. So if you want to learn more details about in-memory full text columns, which, by the way, so leverage in-memory expressions under the covers, and we'll talk a little bit about that today. The city points and the J purchase order are for Json and Spatial. So I populated everything in the column store ahead of time, literally just to save time. I, again, will make the scripts that I used, so you could try this on your own, because all of this comes, other than the Chicago data, which you can actually download, that's a freely available data set. But the J purchase order and the city points are straight out of the Spatial Developers Guide and the Java or the JSON Developers Guide, which I'll have links at the end So I'm trying to use things that you can do yourself. So if you want to set this up in Live Labs or maybe use Developer Days, VirtualBox, download that. All of this is doable. I even have the SSB schema out on GitHub, and I have a link on our resources page. So the point of all of this is that I encourage you to go ahead and try this out for yourself and just see how fast, I won't say cool, but how fast database and memory can make queries over the row store. And so anyways, that's kind of the lead in to all of this. So let me, I always do it in LS because I never want to have to type everything, but and I bet I got a character in there. I did. So I have first just a buffer query. So we have a question. Is this a license feature? So database and memory is a license feature. So it's an option in Oracle speak, which means you have to pay for it. So that's similar to multi-tenant. Well, then you get three PDBs for free. And I should qualify that database and memory is available starting in 19.8. We've done some blog posts and AskTOM sessions with something we call the base level feature. So you can actually use up to 16 gigabytes of column store without having to license database and memory. And everything I'm doing today, everything I'm doing today, you can do in the base level feature. So if you want to try this in your environment, you don't want to do it on a laptop, you actually want to run it on a server, you don't want to pay Oracle initially until you figure out how great database and memory is, base level feature. So, and it's like advanced compression. So it is an option, but you can use a free version of it and actually do everything we're going to do today. So I'm going to let this go while we talk. So again, I encourage questions. Or, yeah, go ahead.
Yeah, I was saying that there's nothing separate for database in-memory expressions on top of database in-memory.
So is there a SQL to confirm we were within the 16 gigabyte column store? Yes. So as I said, we did a base level feature. So in order to enable the base level feature, you set the in-memory _ force parameter, which then prevents you from allocating greater than 16 gigabytes of column store. It works in multi-tenant, and on rack, you can do this on each of the rack instances. So yeah, so we try to protect you. We don't want you to get in trouble with the licensing folks. We want this to be very clear. 40 seconds, wow. Very clear that that you're using the base level feature so you don't have to pay for any licensing issues. So yes. So what I did is while I was talking, I want to make sure I got the explain plan. I ran a query, the same query I showed you, and our expression, if you will, is right there. The first query is just against the row store. So it took 40 seconds. Again, my machine's running a little slower. When I did this morning and yesterday, it was about 25 seconds. So probably because I've got a bunch of other PowerPoint and Zoom running, it's a little slower. But the only point of this was to show that this is what it would run like in the row store. So I always like to point out, and your mileage will vary, but it will always be faster in memory, and we'll see just how much faster. But notice that we didn't do any physical reads, and what I've done is similar to what I do in my other sessions, is I've fully cached the line order table, 60 million rows, in the keep pool in the row store. So this is going to be a memory to memory comparison of the row store versus column store. But I thought I'd just throw this in just to go through, the row store fully cached in the buffer cache. Then we're going to run this in the column store with no in-memory expressions, just as if you just populated it in the column store. And then I'll show you with in-memory expressions enabled and kind of the progression of the speed or performance improvements that you can see with both database and memory, obviously, but then with in-memory expressions, and we'll kind of contrast that a little bit. So, point being, this is fully just a row store. So this would be like our baseline query, if you will. A little slower. I would qualify the 40 seconds as probably ought to be about 25 seconds, but again, the timing is just relative. So we're not doing benchmarking, so it doesn't have to be perfect. So now what I wanted to do was I'll go ahead and run an in-memory query. So no IME. So let's go ahead and do that. Oops, would help if I put
Yeah.
an @ sign there. So again, the same exact query. The only difference being that I have, in the previous query, I basically said no in memory. I said alter session in-memory query disable. So kind of that you can do that with a hint or a session parameter, that kind of normal thing we've showed in the past, where you can actually test a query without having to disable or unpopulate all of the objects in the column store. You can do this kind of dynamically. There are some caveats with that for other features, but for this, it's a perfectly valid test of column store versus row store. So notice that ran in 15 seconds. Table access in memory full shows us we did our query against the column store. And in our session statistics, we see that we've accessed in memory. So we have our in-memory statistics. So we're accessing data in the column store and returning that much faster. So I would say from 25 seconds to 15 seconds, almost not quite a 2x. If you count the 40 seconds, then it's even better than that. So I probably should just use the 40 to make us look better. But realistically, I usually tell folks, you should get at least a 2x performance improvement, and a lot of times much better. I usually say I'm disappointed if you don't get at least 10x performance improvement. But again, we're doing something on my laptop, so our mileage is going to vary a little bit. So, all right, enough talking. Anything you want to throw in there, Auro? I don't want to dominate all of the discussion here. So.
Yeah, so far looks great.
So far, so good.
We're going to run the IME query, and then we'll see it in action.
So what I did, and I did this ahead of time only because I just didn't want to have everybody wait around for us to repopulate the line order table. But what I wound up doing is in order to create an in-memory expression, it's an alter table command. So I said alter table line order. I added basically a virtual column. And then we've set some parameters. And again, you can go back to our other in-memory expressions session. Actually, I guess I could just, since we're.
You got a typo?
Yep. Which is why I script everything. So in our environment, what I've done is I've set in-memory expressions usage to enabled, and in-memory virtual columns, this guy here, to enable. So that enables not only the ability to use in-memory expressions, but to automatically populate in-memory virtual columns that have been defined. If you don't set enable, then you'll have to go in and manually alter table in memory and then specify the column to be enabled for in-memory as well, the virtual column. So it's make life simple. Just set these parameters to enable, and then you don't have to worry about it. So that's the only caveats to, and I don't remember what the defaults are. I think I have it on a slide we'll go back to.
Yeah, the default for the in-memory virtual columns is actually manual. And the reason was that we didn't want people who upgraded from 12.1 to 12.2 to suddenly see the virtual columns being populated, because not every virtual column may be used for your analytics. Some may be used just for partitioning, for example. So that's why we left it as manual, so that users could use the selective column syntax to say, hey, I want this column and this virtual column to go in memory. But of course, for the purposes of demo, and if you know your workload, enable is a perfectly valid mode to use.
Yeah, very good. So, and that would be similar to like if you wanted to exclude columns from the normal columns because they're not being used for analytics and you don't want to take up the space in the column store. And within memory expressions, you just guys decided to do that proactively and let people decide which ones they might actually want, since again, people might have defined virtual columns that they don't want to run analytics with and take up the space.
Yeah, that's a good point, Andy.
So, so all I did was alter the table no in memory, because once I define that virtual column, then we need to repopulate the object into the column store to get this expression, if you will, this virtual column to be populated into the column store. So there's a repopulation requirement. It's not magic. You actually have to repopulate the object, and so I did all that ahead of time. Of course, I talked so long that probably could have just done it on the fly, but again, And then what one of the caveats is, since we're doing this, since we're going to populate this expression, we're going to calculate it for each of the quote rows, but are the column values associated with a given row, since it is a columnar format, it does take space. And so what I have here is a query that shows how much space that V1 virtual column for that in-memory expression took. And in this case, the overall, let's see if I go back, the line order table itself, bear with me, is using up about almost 2 gigabytes of memory. And of that 2 gigabytes of memory, since I've already populated it, oops, could just hit enter, I guess. About 285 meg is taken up by that particular virtual column that we've created. And it actually lives in, we've talked about in-memory compression units, which is the columnar data that we populate in the column store. In-memory expressions actually are populated in something called in-memory expression units. Again, we talked about all this in the previous sessions, which you can go back and take a look at if you're interested. And it's actually documented as well in the in-memory guide. But my point of this was just to show that nothing in life is free. And so you do have to take into account that there's going to be some extra space for in-memory expressions.
Right. And one more point to add here is that you can always use the selective column syntax to define a different compression level for this virtual column. You could go to a higher compression level like capacity high, which would stunt your gains, but you would still kind of trade off the space usage versus the benefits you can.
Actually, that's an excellent point, because as I was doing this, since I only have a limited amount of space on my, I don't have, let's take a look at that right now. Thought I had it on there. So I actually had to, which, we've talked about compression in the past, attributes. There we go, this guy. I actually set for the Chicago data table and the line order table, the one we're talking about, capacity high. So you could do this, so you can set it at the object or segment level, which again, we've talked about, and the trade-off is still way faster than being in the row store. But caveat is that you can also do this at the column level. And I did this because I couldn't get it all to fit otherwise. So, so that's actually a good point. And I did keep the query here so I could talk about or reference to it. But the excellent point is that there may be a case where you decide to vary the compression levels, which a lot of folks kind of think of in-memory or the default in-memory mem compressed for query low, which is the default compression, as being the only one you can use. But realistically, most of our Oracle customers don't run around with terabytes of memory on their database servers that they can allocate to the column store. So the compression options that are available with database and memory can be very valuable, because again, even at the highest capacity high, it's still going to be way faster than having that data be in the row store. In other words, not populating it at all. So there are trade-offs. In my case, I had the trade-off because I didn't have enough memory physically in my machine. You may bump into that or not, depending on how much your workload and how many objects you want to populate and the columns you want to get populated. But yeah, that's a good point, that you can, if you decide that you want to have in-memory expressions, you could choose to populate those at a higher compression level. So good lead in. All right, where were we? I think the point was now, is it any faster with our in-memory expressions populated? And so let's see. So it's the same query, and we'll see how fast it runs compared to before. So 7.6 seconds, and I think I got 4.5 or so when we did this yesterday, and when I did it this morning. It's still in memory, table access in memory full. I don't want for some reason in 21, the execution plans, if I wait too long, they tend to get shoved out of memory. So I wanted to make sure I got that. I did cheat though. So what I did is, even though I have the in-memory expressions already populated. I did make a session parameter to not use it, and so 15 seconds with not using the in-memory expressions, and we showed that to you because we don't have anything. All we've done is in-memory access in session statistics. So in my current environment with the current load on my machine, 15 seconds to run our query in memory. And sorry about scrolling, and with in-memory expressions enabled, 7.6 seconds. So if you think about it, the only difference is that we populated that expression into the column store as an in-memory expression in a virtual column. So we literally cut the response time in half based on that expression, which you would think, wow. So, arithmetic expressions are relatively expensive, relatively in the sense that we can make it a lot faster if we pre-compute them. And so that's kind of the power of the overall in-memory expressions. And this is a pretty simple expression. I don't know if you want to chime in on that.
So one part here is that obviously you avoided the repeated evaluation for every row because you had value cached. And the other sort of thing to note here is that you have a sum there. And now since the expression looks just like a regular column, we can use our in-memory optimizations like aggregation pushdown to push the sum closer to the data. So now every time we look at one of these in-memory columnar units that Andy referred to, we can run the sum on the expression and then just quickly return one row out of there, as opposed to returning all the rows to some function. We're just going to run the sum again and again. So you see two benefits here. One is the avoidance of repeated evaluation, and second is all our in-memory query smarts kick in for the expression now.
Right, and it's kind of funny because I was just looking when we have, and there's a couple other scripts we'll run where we'll look in the predicate field, because obviously there's no where clause in this query. So we don't see any push downs, but the reality is, and we don't show that in the execution plan, but not only do we push down filter predicates, but as you mentioned, aggregation functions, if you will, like sums, mins, maxes, we'll do those calculations while we do the scan in the column store. So that's another benefit. And you're right. So we're able to do that because we're treating it as another column. Good point. And then the other thing I wanted to highlight was, remember I mentioned that with in-memory expressions, we have some additional statistics, and you can see that here. We didn't see that prior to when we didn't have an in-memory expression available to the query. And now that we do, you can actually see that we got some significant benefit from the time, but I guess significant benefit is relative. But here we can see that we did leverage in-memory expressions when we queried our roughly 60 million rows in the column store, or column values, I guess. I mean, ultimately, they wind up getting stitched back into rows, but we tend to talk rows in Oracle, but really we're talking about column values in this particular case. So,
right. And regarding the 2x gains, if you made your expression more complicated, and we have seen sort of certain financial applications having logarithms in there, which can really give you anywhere from 10 to even 100x. We have seen some cases there. So yeah, 2x is the modest end of the number.
Sure, because and it's 2x on top of the performance we gain we went from 40 seconds to 15 seconds. Right. And then we went from 15 to 7.5 seconds. So this is 2x just within the column store query, not 2x over the row store query. So if we actually go from 40 seconds to 7.5 seconds, that's a considerably bigger difference when you're talking the row store in a fully loaded, if you will, column store query. So pretty significant. And again, you're right. More complicated queries, this is pretty simplistic, but we're just demoing more data. If you're looking through hundreds of gigabytes or a terabyte of data. We actually have a customer that has, we've been working with recently, that has over a 3 terabyte column store. So when you get into those kinds of numbers, this becomes much more pronounced as far as the kind of time savings you can see. All right, so I think we've got what I wanted to show with the basics of, see, we're already, I remember I was telling Auro yesterday, we kind of I shoot for 20 minutes and we're already into like 40 minutes. Again, if you have questions, feel free to ask. What I want to do now is, let me go back to the slides real quick. And I'm going to go, so we've kind of talked about all this. I will make these slides available, but we've done all of this. And so what I want to now talk about is what we've done or to leverage in-memory expressions. So there's really, to cut to the chase, there's 3 things. JSON, we're going to talk about JSON, we're going to talk about spatial, in-memory spatial support, and in-memory full text columns or Oracle text support within the column store and searching. And all of these 3 features, which I'm going to demo to you as well, have leverage the in-memory expressions framework and create in-memory expressions under the covers automatically for you to gain or give you some significant performance gains. So I'm going to, we've kind of chewed up a bunch of time. I was shocked when I look at the clock there, but we got plenty of time. We have an hour. So I just wanted to point out that JSON's available in Oracle database. You don't have to have database in memory to take advantage of JSON, and it's been around or so directly supported since 12.1. And the traditional JSON support uses a check constraint to tell Oracle database that you have JSON data, and then there are both from syntactic ability plus from a function ability, you can use JSON in the database, and it makes a JSON database, if you will, within Oracle database perfectly feasible and usable. And so that's kind of part of our converge message and something we work on to allow non-traditional relational database structures to be used within Oracle database, because it's so strong as far as all of the abilities of Oracle database to access data, to use SQL, all of those kind of things. So I don't want to do a sales pitch on JSON, but realistically, JSON in the database has been very valuable for a lot of customers. And then in 12.2, we introduced the ability to then populate that JSON data in the column store. And so this is the part of being able to use in-memory expressions to leverage this. And so this is since 12.2. That's what we talked about in the in-memory or the JSON AskTOM session. So I'm not going to go too far into all of that. We do talk about a little about OSON, which is one of the ways we get big performance benefits is being able to use a binary version of JSON. And that's not a lot different than the binary XML stuff we had before, but JSON's kind of taken over and is much more popular to use. And I'm just going through this pretty quick, Auro, so if you want to throw anything in. And then what we basically do is store that binary version of the JSON in a virtual column and populate that in the column store. So that's really in-memory expressions under the covers, which I'll kind of show you. And then all I wanted to point out was, again, in 21C, we have a real first-class JSON data type as well. So now you don't have to kind of tell us through a constraint definition that it's JSON data. You can actually use a JSON type. And so you can actually tell the database that this is JSON. And the demo that I'll show is going to use that. And then it gives you all the same capabilities. The only difference, I guess, really is that it's because it's part of the row store and blocks, it's limited to a smaller footprint, right? I mean, we talked about this yesterday a little bit. I don't know if you want to elaborate on that at all.
Right. So if you go back to the first slide that Andy was talking about, you could store JSON as blobs, clobs, and varchars, which have their own limits of what data can be inlined, which is 4 kilobytes, and then everything else goes into a separate out-of-line segment. Now, with the native JSON data type that we introduced in 21C, we can store up to 8 kilobytes in the block in line with the row, and everything else goes out of line. So it's not that you're limited in size to 8 KB. You can go up to 32 megabytes for that. But it's just that the inline performance you'll get for up to 8 kilobytes. And one other distinction is that the binary OSON format that Andy mentioned, for this JSON type, you get it on disk as well as within memory, obviously, but you get it on disk directly. Now that could not be gotten for the older JSON specification through the check constraint on blobs and clumps.
Very good point. So that's there is a difference there.
Yeah.
And we'll show you that in the demo. So the only other thing I guess would be maybe the differentiator is if you have larger JSON documents, you might consider not using the JSON data type, or I don't know where the trade-off is there. So I'm not, and again, actually, I'll point you to the JSON developers guide as well, where it talks about that in more detail. But you have any thoughts? And would there be a trade-off there?
So there is a small trade-off, and there's a lot of history behind that I won't go into. Across releases, there's a lot of history.
Sure.
But so basically, right now, if you store the JSON data type in memory or within memory expressions, you're going to get same or better performance than what you used to get with the 12.2 or 18C or 19C old style JSON. And the mechanics of it have been explained in Andy's blog and so on. But yeah, I won't go into that. I won't take more time on that.
And of course, the reason for doing this is you can get very significant performance improvements over not populating this in the column store. And I say 2x to 30x, but I think, as we discussed yesterday, it can be even greater than that. So your mileage will vary. And there is the ability then to take portions of a document and populate that in the column store as well, rather than having to sift through the entire, you can have the entire JSON document, but then if you know you have kind of like our in-memory expressions, if you have certain portions of the document that are heavily queried for analytics, you can actually break out those portions and populate those in the column store as well, correct?
Yes, absolutely. Yeah. So in the little bubble that you see, theater AMC 15, you can pull out all the theater names from this list of JSON documents, and then you can run sort of this JSON value predicates on it. Hey, find me all the movies that are running at the AMC 15 theaters or all AMC theaters. And those will benefit from the core in-memory expressions, because that now is just a relational expression. You've extracted the scalar from within the JSON. And you can see significant benefits over, let's say, walking through the entire JSON and then finding this field and doing the search within.
Very good. Okay, so I'm going to skip over these because I'm going to show you this. I'm going to just briefly mention in-memory full text columns and spatial in the interest of time, and then we'll move into actually showing you this running in the database. But the gist of this is we can take for certain syntax, we can actually put the text index, if you will, that formerly existed on disk. We can populate that in the column store along with your text data and make the indexing access to your particular text phrases that you're searching for much faster. And so that's kind of I've done a pretty detailed blog post, and what I want to do is show it to you, and I don't want to run out of time. So I'm going to kind of gloss over this part, which will just show you right in the query. And then in-memory spatial and full text are kind of the same architecture, if you will, obviously completely different, but under the covers, they're kind of implemented the same way. And so, and I'll show you the syntax, but with spatial, we can now put a spatial index summary into the column store as well, and make the finding points or data based on location much faster with in-memory and spatial support, as opposed to not having that data populated in the column store. Hopefully that's good. And then I'm going to skip out of this, and I'll come back to get to this, only because this is where the documentation is. So we'll finish up with some pointers to some more information if you're interested. And let's get back to, let's try running this. So I wanted to show, so I'll do JSON first. The JSON is going to use a JSON data type. And what I've done is I've I basically just written a SQL script that's going to go through each of the steps, so I don't have to cut and paste everything. And so what I've done is I mentioned the J purchase order table. So we've populated that in the column store. And I didn't have to do anything special because, and I have a describe here, which I think is, I should have done this in a different order. Crud. I didn't do a describe, sorry. So I'll do it in a second. So when I do a describe of the table, we actually have a JSON data type. So, well, we can just do this. I thought I put the describe for the table in the script and I didn't. So the table looks like we have a PO document and we have it defined as a JSON data type. So this is new in 21C. Prior to that, it might have been, say, a varchar or a clob, and we would have had a check constraint on it. But now you can actually store this as an actual JSON data type. So let me go back and restart this. And so what we've done is I just literally just an alter table in memory and populated the table. And this is a list of the columns. And so notice that since we have that JSON data type, we have, you can see as a virtual column, sys IME. So that's kind of the IME is the trigger, and OSON obviously is another clue that what we have is an in-memory expression under the covers. And notice that we're referencing PO document, which is our column that is JSON, so hence the describe. And so we're going to return the data. Basically, we're going to query that virtual column when we do our JSON query. I get that right, Auro?
Yeah. Okay.
Sorry. So all I have is I'm just going to do a count star, so simplistic, but I'm looking for any purchase orders that have a zip code of 99236, which is basically San Francisco. And it turns out out of all of the data, which I didn't do I guess I didn't do a count star. We'll do that in a second. But 4,000 of those documents or purchase orders are in that zip code. So maybe we're doing some analytics on who is purchasing information or purchasing products based on region or something. I don't know, some query that you need. And so within JSON, that runs very, very fast. Oh, here we go. And so that, okay, I'll do the count. I'm out of, so there's two things I need to add to that script. The describe, which I thought I had in there, and then the count of how many rows or column values or documents are in our purchase order in the table itself. So I'll add that. We'll do a count in a second. So the takeaway here is that we ran that query. It ran in 0.03 of a second. We did a table access in memory full. And notice that in our predicate information, which I kind of was talking about for our where clause, we're showing that we're pushing down right there. Notice that we're accessing that in-memory expression, and Oracle's telling you that through the execution plan that it actually accessed. And I'm not going to try to decipher all this unless you want to spend the time on it, Auro. But the bottom line is you can kind of see this, and then with our session statistics, again, we see that we accessed in-memory expressions to look at that. And actually, there you go. So we have 10,000. I remember I took this example literally from the J purchase order orders demo schema, and it's 10,000 rows. That's what I loaded into the database. So out of the 10,000 rows, 4,283 of those, you can actually see that from this statistic here, passed our criteria, and that's what we returned for a count. We might have actually selected portions of the purchase order out of those values in order to do some work on them. But bottom line is fully supported JSON, rooting around in a JSON document in the column store, getting really fast performance. All right. 9:51. Man, I told you sometimes we wind up running a long time, and so I guess I do too much talking. But hopefully this has been interesting. So we're going to do the text one next, and we'll do the spatial. The text one. Remember, I mentioned that I'm using the Chicago Chicago crimes data set. Literally, I just downloaded it. It's a freely available work set. And the reason was that the SSB schema doesn't really have any text in it. There aren't really any useful text. And turns out that it'll be kind of funny when I show you the query. Well, maybe it's not funny, actually. It's probably actually pretty disturbing, but it was a relatively large data set that I found enough text in there that I thought this made a more meaningful example. And so all I did was I mentioned, and I have this in the slides, but what we did is I told Oracle, and database and memory, but Oracle database, that we have an in-memory text column. So that triggers some stuff that goes on under the covers to say, oh, so we're going to have this description column is going to be text. So we're going to create essentially an in-memory text index on that data so we can search through it much more efficiently than if we had to go through, like JSON, if we had to go through the actual text itself. So it essentially creates a nice text index into that description field in the column store. And then I altered the table itself to be enabled for in-memory and then populated the table. And I showed you earlier that that was one of the tables we populated. And so I did a describe here, and we see that we actually wind up creating an in-memory expression as a virtual column under the covers. You can actually see it. This is a user tab calls, which will show you the virtual columns. If you just do a describe, the virtual columns aren't going to show up. And then the query I ran was, as I was telling you yesterday, Auro, where it contains, so to use in-memory full text columns, we use the contains function to access the in-memory index. And so all this is documented, and the example, well, I guess the example isn't, the spatial is, and the JSON is. This one, but there are examples that do this, that do basically the same thing. And again, you can do this on your own in the text developers guide, or the application developers guide. But unfortunately here, with the disturbing part, battery, since this is Chicago crimes, isn't electrical battery. This is, people beating each other up. And so out of the data for this particular district, we see that we had 29,000 hits on text or description with some form of battery in it. And so the only idea here was really just to show that we can search that data very, very fast. The advantage here is that you don't have to then maintain a separate Oracle text index on disk. We can maintain it right in the column store. And so not only do you avoid that, but then we also get way better performance being able to search that data as well. And we see in our table access in memory full. And again, we see that we access that virtual column within the predicate as we did the scan. So we've pushed that predicate into the scan. And then we see again our in-memory expression units. So we know that we did leverage in-memory expressions under the covers to accomplish this. So that's that one. 5 minutes to go. We're going to make it.
You'll be fine.
All right. And then the last example was spatial. And spatial is kind of interesting because now you can combine location information within your relational queries. And so this guy, and this would be out of the Spatial Developers Guide, this is literally just demo data. City points is one of the examples. I literally took the example they use in the JSON Developers Guide and added database and memory to it. And so here, before we did with text, we identified the text column, the document column that was going to be, we were going to create the in-memory full text index on. And then in spatial, all we're saying is we're telling, and I did it all in one command, but we're saying that the shape column is a spatial column. So we want to do special work with that column to create points and index points so that we can access that data as part of our query. And what's interesting here then I populated it again. The key of all this is, since we're using in-memory expressions, is once you define this, you do need to repopulate the object because you want to get those virtual columns that have been created into the column store. But here the interesting part is we created a whole bunch of virtual columns. And what this is, if you kind of look at this, what we're doing is we're taking the X, Y, and Z coordinates and creating min-maxes for them. So we know as we run our query, which I'll show you in a second, that we're locating the point within the data, if you will, to come up with where do we meet. And so to explain that a little bit better, what we have is a query where I have an SDO filter. So there's some restrictions on, again, being able to use spatial with database and memory. One is that it requires a SDO filter function. And within that, though, I'm asking the database, tell me all of the cities within this geometry. And so you can imagine that you might have a application where you draw a box or something around a particular area, and you want to know all of the, say, townships that are within that area. That's kind of simplistic, but essentially that would be the what would happen, or what you could, what demo that you could do. And in this case, we see that for these particular points, San Francisco is the city that we lock in on. And so you might combine that with some other analytics to say, I'm looking for, I don't know, certain restaurants within San Francisco. Are there any Togos or fancy restaurants, maybe Ruth's Chris or something within San Francisco as part of an overall application? You can do all this. The point is, you can do all of this within Oracle database, as opposed to having to launch out somewhere else to go find the spatial information and bring it back. You can all do this in Oracle database. And
yeah, just to briefly expand on that, right? So
sure.
What we are doing there is, with those 6 XY points, we're essentially trying to bound your polygon that defines the shape with a minimum bounding box. So that's kind of like you can think of as an upper bound of what can encapsulate the polygon.
And computer science explanation, yeah.
And that search is essentially a point in polygon search.
Right.
And Andy also brought up a good example regarding restaurants, because I always like to think of all of these features can be used in a converged manner, meaning if you want the answer to the query that, hey, which restaurant has a 4-star or higher rating, serves burgers, and I can find that from the menu, and is within, let's say, 5 kilometers of me, 5 miles from me. It's essentially combining a relational predicate, a text predicate, and a spatial predicate. And you can throw in some JSON in there from like some tweets or something like that. So that's where you can use all of these features together. And this is where the real power comes from, the sort of the infrastructure that in-memory expressions provide to provide convergence within the Oracle database.
Well said, well said. And then we have our filter predicate, and we access the table in memory. We have our session statistics, where we actually, in this case, I don't have very many rows, but we used our in-memory expressions underneath the covers, and we made it 10 o'clock, right on the money. I don't see any other questions. And we can stay for a minute or two, see if anybody has any questions. That ran quite a bit longer than I anticipated, but we got through everything. And I think it's quite interesting. I think that's very succinct is what you said, that is the converged database combining all these different data types that might not be traditional relational data types to actually create real applications, and not having to have all of these specialized databases where you have to fragment your data in order to get it into the format that your application might be able to make use of. So being able to do all of that in Oracle database, and obviously for us, being able to use database and memory to make it way faster so that you could realistically do this on the fly, as opposed to having to pre-compute everything and not have it available to do, say, just ad hoc type queries. So.
Yep.
And with that, I don't see any other questions. I want to thank you very much, Auro, for attending. I want to thank everybody else for attending as well. And we will have a recording of this. Oh, I promised to. So all of this information is covered in the in-memory guide, our spatial graph developers guide, the text application developers guide, and the JSON developers guide. So you can go back and, if you want to try this out on your own, and then our resources page, where I have a link to our GitHub repository, which I will actually put the scripts and this presentation PDF out there, which I haven't been doing, and I'll go back and do some for our other AskTOM sessions as well. And if you want to try this out on your own, Live Labs, the base level feature, which we had the question earlier about, play around with it and see the kind of the value you can get from database and memory. And with that, I think we're done. Thank you very much, everybody.
Thanks, everyone.